So number 4, this problem number 4, in a lottery game, a player picks 6 numbers from 1 to 20, right? If the player matches all 6 numbers, they win $30,000. Otherwise, they lose $1, right? So we've got to look at the odds of winning, right? So the odds of winning um, is picking all 6 numbers out of 20, 5 numbers out of 19, right? 4, 18, 3, 17, 2, 16, 1, 15, right? So the odds of winning are 720 over $27,907,200 or 200, right? Not $200. Now the odds of losing, where did this number right here? This number right here, huh? Yeah, denominator did. All right, so how did I get that number? That number came from this. If I take the total, right, my denominator is really um, okay, let's kind of think of it like, I guess the easiest way to be able to think of it would be like uh, factorials, right? Combinations, I guess combinations, yeah. That many different combinations. You have that many different things that you could do, right? So so 27,907,200 minus 720 would give you your odds of losing, right? So you have a greater odds of losing than you do of winning, right? So this one is based off of odds. Okay. What are my odds of winning? So it's a little bit different than probability. It's still probability, but it's odds, right? I don't know how to explain that to clear that up, but just look at it. So here's 30,000. Here's my odds if I win, right? Minus my dollar, right? Because I lose $1 if I don't win, right? And there you go. So don't keep them as a decimal. Keep it as a fraction. Because if you do a decimal, it's going to give you a small number, right? That's probably going to have an E. And hold up for a second. Y'all good? All right. So my expected value is that I'm never going to come out ahead in playing the lottery, right? I mean, how many people do you know? Let me hit this, and then we can have a conversation. It's kind. This is number 5. It's kind of like the concept, but it's taken into probability, right? Multiple events, expect value over multiple events. So we look at the probability of getting a gold and how much we'd win, plus the probability of getting a silver and how much we'd win, plus the probability of getting black and how much we'd lose, based off the marbles that are being selected from a bag of 34 marbles, right? So if we play this game, we we're expected value back is 6 cents. So did it even say? It didn't even say how much we got to play, right? So it ain't worth 6 cents. Does that make sense? Okay. And all these games are, they have an expected value that you come out. Now you may win big, right? Don't think you won't, but you also um, have a higher probability of losing. So All right, next. So this is number 6. Person must play. On my problem, it says person must pay $4 to play a certain game at a casino, right? The probability of winning is 0.15, which is 15%, right? And it's probability of winning $14. Now, excuse me. If you have to pay $4 to win 14, how much are you really gaining? That's right. That's why it said net gain of 10, right? So your probability of winning is a $10, right? Now your probability of losing is 0.85. And you're going to lose how much it costs you to play, which is $4, right? So if you go down here and you set up the equation, expected value equals, here's the probability of winning, right? 0.15 times the $10, which is how much you'd win, plus if you lose, right? And that's why the 4 is negative, right? Which gives me a negative $1.90. That's my expected value. Yeah, it's negative. Yeah. Now, if it was to come out to be positive, then he'd be ahead. Well, depends on theoretically how much he's going to, get back, right? If his expected value is greater than the um, cost to play the game, right? Expected value is greater than the cost to play the game, then um, they can they'll make more, they'll make money, like more money. So, all right, next. So this is number 18. So it's just like the ones that or with the ones that say, hey, you got a marble bag full of blah blah blah. So they list them out, right? 24, 44, 27 for a total of 95 marbles. 24 of them are red, 44 of them are blue, 27 are green. And if you hit a red, you get $9. If you hit a blue, you get 7. If you hit a green, you get 6, right? So what they did is compute the probability of winning a 9. So they asked you those 3 things. They asked you each probability for one of them being a red, blue, and green, right? That's what this 0.253 and 0.463 and 0.2484, right? That's where that's coming from. So what they're doing is they're individually asking you these probabilities. So that's what goes in these first 3. And then you multiply plus multiply plus multiply, right? And you get $7. On mine, I got $7.22, right? And I'm not sure if it asked. Yeah, it didn't ask, but it did say use the values above to three decimal places, right? So please be aware of that. Okay. All right. Secure, you good? Here's number 20, and it's the spinner, right? So let's look at how many different spots we have on the spinner. There's 4 spots, right? So each one of these dollar values has a 1 out of 4 chance of hitting it, right? So the probability of hitting a 9, 6, 8, or 5 are all 1 out of 4. Okay. So that's where for me, that's where the 1 out of 4 came from. Now, that's the probability of hitting a 6, probability of hitting an 8, probability of hitting a 5, and probability of hitting a 9. When you do that, I got an expected value of 7 on my example, right? Okay. Any questions about how I set up this? It's probability times the value, probability times value, probability times value, so forth, right? Summation of those. So, are the outcomes equally likely? Yeah. Each one of these has the same probability, right? Because it only showed up one time out of 4 choices, right? Hence why we did probability before we started all this. Now, here's the question. If you run this game and you charge $7.50, and my expected value on my problem was $7, right? Would it be considered to be a fair game? If it is a fair game, that means the summation of those, with one of them being the cost to play being negative, the summation better be equal to 0. Your cost to play and your expected value, if they are the same, it's a fair game, right? Meaning they're not going to win anything off of you, and you're not going to win anything off of them. It is as fair can be. Now, so I think this first one is, wait. It's either a yes or a no, right? And for this, it's no, because my expected value is 7. It costs to play $7.50, right? Now, why is it? Because the cost to play is greater than the expected value. Okay. I could have put the expected value is less than the cost to play, right? But I think your choices are, I don't know what your choices are. Let's sit here and go. I think your choices are, the cost to play does not equal the expected value, because the cost to play does not, the cost to play does equal, and we have no way to know if the spinner's fair. The spinner's going to be fair, because the person running the game is going to lose money on people who play. Not if they charge $7.50, they don't, right? Not if the cost to play is greater than 7, right? So those are the things. Because the cost, this is not a fair game because the cost to play does not equal the expected value. Oh, yeah, does not equal. That one said does. It'd be the top one. The cost to play does not equal the expected value. Okay, that'd be why it's not a fair game. If it does, then it's a fair game, right? Okay. All right. Any questions?